Σήμερα είμαστε πολύ χαρούμενοι να έχουμε την Παναγιώτα Καντή μαζί μας από το Πανεπιστήμιο Ιωαννίνων. Η Παναγιώτα δουλεύει σε μαύρες τρύπες, φαινομενολογία από μαύρες τρύπες και extra dimensions για ένα διάστημα, σε ακριβείς λύσεις, numerical και αναλυτικές λύσεις. Πήρε το διδακτορικό της από το Πανεπιστήμιο Ιωαννίνων από τον Κυριάκο Ταμβάκη το 1998, την ίδια χρονιά μαζί, είμαστε συνομήλικοι σε αυτό, και μετά έκανε μία σειρά από postdoc στη Μινεσότα, που δούλεψε με τον Keith Olive, ας πούμε, στην Πίζα, στην Ιταλία, στην Οξφόρδη, και κατέληξε, όπου εκεί τη γνώρισα, να είναι σε μία μόνιμη θέση, αφού πήρε ένα P-Park Fellowship για 5 χρόνια, στον Durham, όπου κάθισε 4-5 χρόνια, αν δεν κάνω λάθος, για να επιστρέψει μετά, εδώ και από το 2004, Παναγιώτα, 2006, στα Ιωάννινα, που είναι καθηγήτρια. Σήμερα θα μας μιλήσει, ο τίτλος τον βλέπετε μπροστά σας, From the Black Hole Through the Wormhole to Ultra Compact Objects. Οπότε ας ξεκινήσουμε.
Thank you very much, Christos, and thank you all the governing board of the society for their kind invitation. It's an honor for me, and it's a big pleasure. This is indeed the title of my talk. Let me go forward to the outline. So I will give a brief introduction, which is a motivation why we should like to move from GR, general relativity, to generalized theories of gravity. I will focus on a particular theory, which is the Einstein scalar Gauss-Bonnet theories, as with the plural, because we are going to consider a variety of theories. And in the context of this class of theories, I will look for black hole solutions, wormhole solutions, and particle-like solutions. So for different gravitational solutions. This talk is based on a number of works which have appeared in the last 3 years or so, and they were done in collaboration with Yorgos Antoniou, now a PhD student at Nottingham University, Athanasios Bakopoulos, who was until last summer my graduate student at Ioannina University, Burkhard Kleihaus and Jutta Kunz from the Oldenburg University in Germany, and Nikolaos Papas, who was at the time a postdoc in Athens University. So, starting my introduction, we know that Einstein's general theory of relativity, which is based on his field equations, his famous field equations that have this particular form, describes extremely accurately the gravitational field around ordinary astrophysical bodies, such as our Sun, but also it predicts the existence of additional solutions, which are considered to be slightly, or were considered to be slightly exotic, like the black holes or the wormholes. It is definitely a very beautiful mathematical theory. However, very few people consider GR to be the final theory of gravity due to a number of problems that we have encountered during the last 100 years that we are studying this theory. For example, we have the dark matter problem, the dark energy problem, the coincidence problem, the initial singularity in the universe, the non-unification with the other forces, etc., just to mention a few of those. Therefore, we need, due to these reasons, to move beyond GR. But there is also another reason, because general relativity is a rather restrictive theory from the point of view of new gravitational solutions. Of course, it's a much richer theory than Newtonian theory of gravity, Newton's theory of gravity. However, it is not as extensive, as rich as we would like. For example, it admits, of course, black hole solutions. It predicts the existence of these very exciting objects in the universe, but only 3 families of those. We know the Schwarzschild family of black holes, the Reissner-Nordstrom, and the Kerr-Newman. There have been a number of Noether theorems formulated over the years. The oldest ones say that these black holes are characterized only by 3 quantities: the mass, the electromagnetic charge, if they have a force, and angular momentum J. Beyond those, we can find no other charges, let's say, which characterize these black hole solutions. For example, they have no color, baryon number, lepton number, or even scalar charges, which will be the focus of this particular talk. And I will come back to that later. Of course, it does admit wormholes, as we will see later on, because they are hidden in the interior of all black hole solutions. However, these are not very realistic. They are not traversable wormholes. Of course, we don't have yet the final theory of gravity, the quantum theory of gravity, because we want to achieve unification with the other forces at very high energy scales. However, in the absence of such a theory, we may consider something in between. We may consider effective theories of gravity, modified, of course, that include the theory, the general theory of relativity, but they have also extra fields and or higher gravitational terms. For example, a generalized theory of gravity, or alternative or modified, you may call it as you like. Such a theory would have this particular form. For example, it is not a complete action that describes all of the modified, but it is one particular prototype. So in the action, we may have not only R, as we have in Einstein's theory of gravity, but also we can have other gravitational terms, and we can have a number of additional fields. Of course, there is a plethora of modified theories of gravity in the literature, and I have named a few here, for example. I have probably missed some of them, so it is not an exhaustive list. And what is the hope for all these theories? Such a modified theory may describe more accurately than GR the stronger gravity regime. This is a regime that up to recent times was not studied, and we are now slowly starting to explore. We may derive constraints about the strong gravity regime from neutron star properties, gravitational waves, as they were recently detected by LIGO and Virgo. We now have bounds from the Einstein, from the soon to come, from Einstein telescope, but currently from the Event Horizon telescope, and etc. If therefore we consider a new theory, a modified theory of gravity, can we find new black hole solutions in the context of such a theory? Are we sure that the new theory will be richer from the point of view of gravitation solutions compared to GR? And if so, what happens to the old GR solutions, which we know exist in the universe, and we have already observed them, like the Kerr black holes? From the theoretical point of view, there were obstacles right from the beginning, because they were non-existence theorems formulated from the 70s. I will focus in this particular case on the scalar no-here theorem, which was formulated by Bekenstein and Teitelbaum in 1972. That particular theorem excluded novel black hole solutions with a scalar charge, as it was called, in minimally coupled scalar tensor theories. And almost 20 years later, that was extended to non-minimally coupled scalar tensor theories. In the more recent years, 2012 and 2013, there were two new formulations developed by Sotirio and Faraoni and Hui and Nicolis, which covered some more modern, let's say, scalar tensor theories like F of R theories or Galilean shift symmetric gravitational theories, scalar tensor always. Of course, these particular existence theorems demand a number of requirements in order to be valid. As soon as we change some of the requirements or evade some of the requirements, these non-existence theorems do not hold anymore. And therefore, it is no surprise that we have found new black hole solutions. For example, solutions with the Skirm field from the 80s, with a conformally coupled scalar field by Bekenstein himself in 74, dilaton field in 1996, and a Gates field a bit later, rotating versions, and of course, shift symmetric Galilean black holes, okay, emerged in 2014. So we do have black hole solutions coming out from these modified theories of gravity. In this work, I'm going to consider a very simple modified theory of gravity, one which contains the scalarity term, this one, a kinetic term for a scalar field, and a term which describes the coupling of the scalar field to the higher derivative, the quadratic Gauss-Bonnet term, which is given by this definition right here, is the well-known combination of the Riemann tensor, Ricci tensor, and the Ricci scalar. This we consider to be a legitimate modified theory of gravity. Why? Because such a theory arises as part of the string effective theory at low energies. It also arises as part of the effective theory in 4 dimensions, starting from Lovelock theory in higher number of dimensions, but also it is part of the modified scalar tensor like the Horn-Desky or the Dawes theory. Why it is a promising theory for an effective theory of gravity? Because it contains a quadratic gravitational term, which we think is the next important term in strong curvature regimes. In places where the curvature is very small, of course, this Gauss-Bonnet term is bound to be very small and it's negligible. However, when the curvature becomes important, we expect quadratic corrections in curvature to appear, and this is such a term. Although looks complicated, it has a very important advantage that the field equations that come out of this theory, they have up to second order derivatives of the metric functions and the scalar field. Also, they have no Ostrogradsky instabilities. So this is the theory we're going to focus. And I'm going to look for different type of gravitational solutions in this particular theory. I'm going to start with black hole solutions. Can we find novel black hole solutions in the context of this theory? And for what forms of the coupling function? Because we have a coupling function f of phi, which was left arbitrary. I'm going to look for static, spherically symmetric black hole solutions, which is the simplest kind. And the line element is going to have this particular form. I'm going to have 2 unknown metric functions. And then the equations of motion in covariant form look like that. We have the equation of motion for the scalar field, where, as you see, the Gauss-Bonnet term produces a source term for a non-trivial scalar field. And of course, we have the field equations for the gravitational field. T mu nu, the energy momentum tensor, receives contributions both from the energy momentum tensor, the pure energy momentum tensor of the scalar field, but also from the Gauss-Bonnet term. Now, F is here the coupling function between the scalar field and the Gauss-Bonnet. If that is a constant, and I should stress this now, if F is a constant, then this contribution vanishes. This is because the Gauss-Bonnet term is a total derivative in 4 dimensions, and therefore, if we don't have a coupling with the field, it just drops out from the equations. Of course, here I'm going to assume that f is not a trivial function, but instead a function of the scalar field. The field equations are quite complicated. At the end, we can see, and of course I will leave out the technical details, that one of the 2 metric functions is a dependent one, in the sense that if I find the solution for A and the solution for phi, then I know what is the solution for B. Therefore, what we do is that we take the system of the field equations, and from that we take a system of 2 independent, coupled, of course, field equations for the metric function A and the scalar field phi. Because of the complexity, we need, in order to find a solution for a black hole, we need to numerically integrate. But before doing that, we can do some simple gymnastics in the asymptotic regimes. First, I'm going to ask that I can take an asymptotic solution at the small r regime, which describes the space-time around the regular black hole horizon. So I will demand that the GTT minus GTT metric function e to the a goes to 0, e to the minus b goes to 0, and phi goes to a finite value when r goes to some particular value rh, and that particular value will be the horizon radius. If I go back to the equations of motion, to the field equations, and demand that the second derivative of phi is also finite at the horizon, then we find a constraint on the first derivative of the scalar field right at the horizon. It is given by this expression, which is fairly simple. And if I choose, let's say, the value of f, then I know what the value of that quantity is at the horizon, and I can substitute it here, and I find directly the value of the first derivative of phi. We also take another constraint that the quantity under the square root must be smaller than 1. Okay. Must be positive. And that takes the form that this quantity must be smaller than 1. And finally, this constraint right here. I will come to that constraint later on. At large distances from the horizon, I demand that we have an asymptotically flat limit. Okay. And then, fairly easily, this is what we take from the field equations, indeed. We take a solution which at the lowest order looks very much like this Bartzel solution, but right at the next order, we have the appearance of a new quantity apart from the mass of the black hole, which is d. D is the so-called scalar charge, is the coefficient which appears in the expansion of the scalar field at large values of the radial coordinate. It is the coefficient of the 1/r term, the monopole term. We can see that we don't really need to choose any particular forms for the coupling function in order to guarantee the emergence of a regular horizon or the emergence of an asymptotically flat limit. Of course, the dependence on f exists, but I cannot really exclude or being obliged to choose a particular value for f. The question, of course, is whether now I can smoothly match these two asymptotic solutions in order to create a complete black hole solution. And this is where the Noether theorems usually enter. Because Bekenstein's Noether theorem, the novel formulation from 1994, dictated that the matching of these two asymptotic solutions, although I can find these two asymptotic solutions, these two solutions cannot be smoothly matched if a requirement is obeyed. And this requirement is that the RR component in mixed form is negative near the black hole horizon. Does this requirement hold in the case of the Einstein scalar Gauss-Bonnet theory? Actually, no. One can see fairly easily that the sign of this quantity at the horizon is minus the sign of the quantity f dot, and the dot here means the derivative of the scalar field with respect to the field, times the first derivative of the scalar field with respect to the radial coordinate at the horizon. But this quantity, we know its sign because it is dictated by the constraint we had before for the first derivative of the scalar field. I'm sorry, I hope I don't make you dizzy. Sorry. It's right here. That is the quantity. If I take the fh dot on the left-hand side, then whatever is on the right-hand side, we can see that it is strictly negative because it is -1 plus minus the square root of 1 minus something. This is smaller than unity, and the combination of that is definitely smaller than 0. So if this quantity is always negative with a minus in front, the TRR component in this particular type of theories is always positive. Thus, one basic requirement for the validity of Bekenstein's Noether theorem is evaded, is not satisfied anymore. And that, of course, opens the way for finding. This is not enough for constructing a black hole solution. What it says is that there is no theoretical obstacle for the existence of these black holes, but it doesn't say that we have definitely a solution. That will come from the numerical integration of the field equations. That analysis was actually followed in 1995 to prove that the dilatonic theory, which had a particular coupling function between the scalar field and the Gauss-Bonnet term, and that was the exponential dependence, the exponential function, it did evade Bekenstein's theorem. And this is how we demonstrated the existence of the dilatonic black holes. Sorry, this is 1996. I made a mistake with the date. So that was a long time ago. And that was the outcome of the collaboration between the Ioannina and the Oxford group, with these people taking part. And the natural question is, if now I go to the case of the Einstein scalar Gauss-Bonnet theories, in which F is arbitrary and can take other forms, potentially, can we find new black hole solutions just like the dilatonic black holes of 1996? So what we had to do is try and numerically integrate our field equations. We chose different forms for F. We chose just a value for the scalar field at the horizon, and we integrated outwards from the horizon all the way to infinity. And as for the first derivative of the scalar field, we just took that from the constraint. It was a very particular value. The constraint for the existence of a regular horizon gave us right away the value for the first derivative of the scalar field at the horizon. So it gave us one of the boundary values at the horizon for the integration to start. And this is what we obtained. This is the metric functions, the GTT going from 0 asymptotically to 1, and the GRR goes from plus infinity down to 1, and that is the non-trivial scalar field. So we obtained a black hole solution, a complete one from the horizon all the way to infinity with a non-trivial scalar field. Of course, there is a huge literature on different types of black holes being derived, or other type of solutions, neutron stars. It is really a huge one, and I couldn't really even start citing all these people. So apologies if you have done, and I'm sure many of you have done things on that. I'm going to cite only the most very relevant for this particular work's publication. So I have actually to mention that almost simultaneously 2 additional works appeared in the literature, which considered 2 different, slightly different forms for the coupling function. So the work by Donova and Yazadziev considered the case F is 1 minus e to the minus phi squared, while the work by Silva and collaborators had the quadratic. Now, that was actually a case that we considered. It is the green curve right here. And of course, we agree on the results. Now, these 2 works discussed spontaneously scalarized black holes, which means black holes with a scalar field emerging when a GR solution is destabilized. And that was, of course, the scalarization process introduced by Damour and Esposito Fares in 1993, first in the context of neutron stars. There was a slight difference between our analysis and this particular analysis, because here it was demanded that the GR solution emerged side by side in the context of the theory with the Gauss-Bonnet term, with the solution that was the scalarized one. Whenever the GR solution was destabilized by the scalar field, then a new solution with a non-trivial scalar field emerged as the more stable one in the theory. In our case, however, are naturally scalarized in the sense that we don't demand GR solution to appear, and that's why we don't restrict our analysis for a particular regime of the parameters of the theory, which is the regime for which the GR solution gets destabilized and then we get a scalarized solution. In our case, we don't impose any constraints on the parameters, but the solutions, as we said, are naturally scalarized. They have always a non-trivial field. The GR solution may exist, in this case, the Schwarzschild solution, because we don't have any other quantities characterizing the black hole, may exist as an independent solution, depending on the form of the coupling function, or it may not. What happens then to the GR solution? Does this mean that we won't observe solutions that look like the GR ones? Of course we do, because in the limit of large mass, all Gauss-Bonnet black holes reduce to the Schwarzschild solution. I have here at the left plot the form of the scalar charts in terms of the mass. Now, a non-vanishing scalar charge means that have a non-trivial scalar field. But we observe that as the mass of the black hole increases, the scalar charge goes to 0, which means that if I discuss large Gauss-Bonnet black holes, these reduce quite smoothly to the Schwarzschild black holes. So large Gauss-Bonnet black holes are Schwarzschild black holes of GR. Or if you like, extremely small Schwarzschild black holes are Gauss-Bonnet black holes. So when the black hole is large and the curvature around it is small, the whole thing reduces to GR. When the black hole has a small mass and thus the curvature around it is rather large, then the Gauss-Bonnet takes over and creates also the scalar field, the non-trivial scalar field. So the GR solutions are not discarded, it just they come out as a particular limit of the black hole solutions, of the scalarized black hole solutions that we have found. Another thing which comes out from this graph is that D is not an independent quantity. So we have found solutions with a non-trivial scalar field, but that scalar charge is not a novel quantity, is not a new conserved quantity which characterizes the black hole. As we say, this here is secondary. It is a function of the mass. The entropy of the Gauss black hole may also compute it, and this is what I have here. The dots in orange color are different black hole solutions corresponding to different mass, and they signify here the entropy of the particular black hole. The blue dots is actually the size of the area of the black hole. It is the ratio of these quantities compared to the Schwarzschild solution that I have plotted here, that have been plotted. And as we can see, we have solutions, Gauss-Bonnet black hole solutions, which have an entropy ratio larger than 1. This is where the unity is.
Panagiota, may I interrupt you?
Of course.
There is a question from one of the participants, and I thought maybe you could. So Vasilis Paschalidis, he can either ask it straight away, or can you read?
Yes, I would be glad to hear it because I don't know how to open the chat.
Yeah, I can ask the question. So what I'm interested in, I mean, I can see on your plot that you have divide the mass of the black hole by a to the 1/2, but I'm just trying to understand whether the statement is a generic statement that when you always increase the mass of the black hole, you always recover GR solutions. And in the generic case where you have an f of phi function, what is the mass scale that determines how small or large is a certain black hole? So is it some kind of a derivative of f with respect to phi, or is it something else?
Okay, now here we have divided with A, which is A here, I'm sorry, I didn't say that, is the coupling constant in F, in the expression of F. We may say that F of phi, I can write it as alpha, which is the coupling constant, the dimensionful coupling constant, and F tilde, where F tilde then is a dimensionless quantity, and I can actually ignore. I can give it forms like the exponential or polynomial or anything else, but its value is just a number. So in order to be able to compare different cases, in order to make, to draw conclusions independent of the value of how large or how big the mass is, that's why you are dividing with A, so that I work with dimensionless units. Now, this particular form for D as a function of M holds for one particular family of solutions. That was for the 1/phi. The same selection for the coupling function for which we have plotted the entropy and the area of the black hole. If I consider different forms of F, then that can have a much different form. It may be even non-monotonic, but no matter what it does in the small m regime, when I increase the mass of the black hole, it always goes to 0. So that is a very generic behavior. Whenever the mass is big, the curvature is small, the Gauss-Bonnet term is small, and that's why the Gauss-Bonnet term is small, and that's why the source term for the scalar field dies out, and I take phi just a constant, both near the horizon and of course far away, where it dies out in any case. So that is a generic behavior, definitely. For small m, in the small m regime, however, it may have a different behavior. Now, where the transition takes place between the Gauss-Bonnet and the Schwarzschild, well, I can't really say that. We're trying to find a way of quantifying this, but it was such a smooth transition that we cannot really say where it stops being a Gauss-Bonnet black hole and being a Schwarzschild black hole. The transition takes place quite smoothly. I mean, strictly speaking, a Schwarzschild black hole becomes right when d equals 0, but the transition from that particular limit, when m is very, very large and d is almost 0, towards the opposite direction is extremely difficult to say. So we haven't been able to quantify that, and I can't really give an answer to this question. But the transition is so smooth that we didn't really bother much on deriving a mathematical constraint on that. I don't know if I answered the questions.
Yeah, you did. Thank you.
You're welcome. Okay, so what I was saying about the entropy is that we can find a whole classes of Gauss-Bonnet black holes which are more stable than the corresponding Schwarzschild solution. And you can see here that all dots corresponding to different Gauss-Bonnet black holes are above unity. And here we have another property of these Gauss-Bonnet black holes is that the Gauss-Bonnet black holes are always smaller than the Schwarzschild black hole for the same mass, which means that the same mass needs to be squeezed more into producing in order to produce a Gauss-Bonnet black hole. That's why there is also a minimum mass. That line here, this curve here, the line of dots actually stops abruptly at this particular point. The same up here. Of course, it stops at exactly the same point, which is a minimum mass for the Gauss-Bonnet black holes. So the Gauss-Bonnet black holes cannot have arbitrarily small mass as the Schwarzschild black hole does. Instead, it stops abruptly at a point. There is a minimum mass or a minimum horizon. It's the same thing. Now, if I modify the theory a little bit by adding a negative cosmological constant in the theory, then of course the space-time reduces asymptotically to an anti-de Sitter background, but the whole process works in exactly the same way. The constraint for the regular event horizon gives us again a constraint on phi prime. We were able to find solutions for all types of different forms of coupling functions that we assumed. It was as easy to derive them as in the case of the asymptotically flat case, and this is the dependence for phi. It doesn't go to a constant in this case. At large distances, apart from a constant term, I do get higher order terms, but we also get a logarithm. So we don't have a scalar charge in this case. I cannot define a scalar charge. And this is typical for the anti-de Sitter background. The next interesting thing that we did, because we tried several different things, was to promote this negative cosmological constant to a dynamic potential. So we multiplied lambda, the constant, the cosmological constant, now by V of phi. So lambda now is just a coupling constant for this dynamic potential for the scalar field. We consider different choices for F and now different choices for V. So the flexibility of the theory was increased now. And again, black hole solutions arise with no difficulty, with a regular horizon and a non-trivial phi. here we give a plot for the dependence of phi, which is typical for almost all of the coupling functions and the phi. I list here different polynomials, phi squared, phi to the 4, phi to the 6, and so on, for the scalar potential. And what I get is that we get an oscillatory behavior, which reduces to a zero scalar field, and thus it dies out at large distances, all by itself. We never demanded this to happen, but the scalar field dies out, and the metric goes to an asymptotically flat limit, even though we do have a potential for the scalar field. What form of solutions we take? Well, we do get a typical black hole, so the metric functions have the same similar behavior as we had before, but now we get different branches. If I take the plot of the horizon radius with respect to the mass, then we can see that we can take different branches for all polynomial forms for V of phi, but we have a distinctly different behavior for the quadratic potential. So the blue dots are the black hole solutions that we get for phi squared. I'm sorry, it's a bit small here. I hope you can see it. So this is the phi squared, and this are all the higher polynomials for V of phi. It is different. Something is different for phi squared. And what happens in that case, and that was the interesting class, so I will focus on that, was that as we see, we have two groups of solutions. We have black hole solutions, which have a horizon radius larger than the one that would hold for this Schwarzschild, let's say, black hole. So we have large horizon, but which correspond to the small mass regime. And then we have small in terms of the horizon radius black holes, but with a very large mass. So either we have large, but not so massive black holes, or either we have very compact and extremely massive black holes. And this is what we called the ultra-compact black holes. And this is a type of solution that we encountered here for the first time, and we thought that this particular property was interesting. So that was the black holes in the case, a small review of some of the most interesting solutions that we got. Now, let me now go to the wormhole solutions. They're very well motivated objects because in GR, they hide inside the horizon of a black hole. For example, the region inside the horizon of a Schwarzschild black hole, we know that we will end up in a singularity if we enter the Schwarzschild horizon. However, not for all times, the interior is dynamic, so a tunnel appears after a while, it expands, and then it contracts again, and then it disappears. Unfortunately, it's not a very useful wormhole because it opens and closes so quickly that not even a photon can pass through. The other solutions of GR, describing black holes, the Reissner, Nordstrom, and Kerr, also have internal tunnels, like this one. However, they are unstable. They don't open and close. Unfortunately, they are unstable because they both have an internal Cauchy horizon, which turns into a black hole singularity once they get disturbed. Morris and Thorne did a very prominent work in 1988 when they disconnected completely the wormhole from the black hole. So they used a fairly simple ansatz of this form with two particular functions unknown, phi and b. They demanded that asymptotically both functions go to zero, so we take an asymptotically flat limit. They demanded that there is no horizon or singularity, so that I don't have problems like the ones I mentioned before with the usual black holes. And they demanded the presence of the throat. In other words, B can take up to a minimum value, let's say R0 or B0, which is equal to a minimum value of the radial coordinate. However, in order for such a solution to be a solution of the field equations by Einstein, it was necessary to have a very exotic energy momentum tensor. That particular energy momentum tensor satisfied that T, the radial pressure, had to be larger or equal compared to rho, and that led to a violation of the energy conditions. Of course, that opened a very big direction of research. in wormholes. There was a large effort in the literature to produce such an exotic but yet realistic distribution of matter. In the context now of the Einstein scalar Gauss-Bonnet theory, it is very easy for someone to observe that if we compute the total energy density and radial pressure which is produced in this theory, then rho comes out to be negative and P comes out to be positive. And that rho plus P is always larger than rho because of that. Therefore, the Gauss-Bonnet term, quite naturally, being a gravitational term, quite naturally creates the effective energy momentum tensor that we need in order to support a wormhole. And indeed, in that early work in 1996, we had discovered a solution which, after a coordinate transformation, may be written in this form, where e to the a and e to the b are polynomials in terms of this radial coordinate L. Also phi is well behaved. The only thing is that when L equals to 0, this radial, this coefficient here, doesn't go all the way to 0, as one would expect if we had just an R square in front, but there is a minimum value, L equals 0 or R equals 0, and this is the throat of the wormhole. Apart from that constraint, everything else is regular. And that is indeed a space-time describing a wormhole. At large distances, what we get is that we get an asymptotically flat limit, quite similar to the one for the black hole. And this is what we discovered in a publication in collaboration with Berger Kleihaus and Jutta Kunz in 2011 and 2012. That solution also has a non-trivial scalar field, as you may see here, and we obtain a traversable wormhole in the sense that particles can pass through the throat to the other side and come back again if they like, which is quite important. There is, of course, a point which is rather important, that as you can see here, all the plots cover only the positive L regime. Of course, that covers the case, the regime from the throat to plus infinity, but I should have the other regime too, from 0 to minus infinity. And in order to create that, what I should do is that I should introduce a fluid around the throat, not an exotic one though, a perfect fluid, a dust may do the work. If I also take into account the curvature of the space-time around the throat. So by adding in my theory this particular action, which is a -1 dimensionality, is a 3-dimensional one, in that case, plus a perfect fluid, I can create a symmetric and regular wormhole, like this one. Now, all these came from the work done in 2011, and a particular form of the coupling function was assumed, the exponential one. So these were dilatonic, if you like, wormholes. Now, if I consider other forms of f of phi, and I may consider maybe a slightly more general line element, then yes, I can find regular wormhole solutions for every form of f. Whatever happened for black holes, I can take it also for here. I can take for every form of f a wormhole, a regular wormhole solution. I can even get richer structure around the throat. I can have 2 throats, which are the minima here, and an equator, which is the maximum here. And this is something that we haven't discovered in the early case, in the early study back in 2011. And that is the domain of existence, where we can see that we have really a large number for every particular choice of f. I can have a very extensive domain of existence for the wormhole. It is not one particular solution, but we can change we can vary the range of the parameters and quite extensively and still produce wormhole solutions. And let me go on to the last part, which are the particle-like solutions. Now, of course, particle-like solutions are very common in flat space-time. They're usually termed solitons. we know about them. And now gravity allows for similar solutions, but however, they do not always have attractive properties. For example, if I consider Einstein's scalar theory, which means the Ricci scalar plus a simple kinetic term for the scalar field, then I can get a solution which has a non-trivial scalar field, a particle-like solution. And that is the Yanis or Janis, I'm not sure how to pronounce that, Newman-Winnicott-Wyman solution, which was produced back in 1968. That was singular because, as you can see, there is a singularity in both metric functions when R becomes M over 2S, and the same singularity appears also in the expression for phi. If I check the curvature invariance, that singularity is not a horizon, is a true space-time singularity. That's why I called it a singular solution. But it is a solution with a non-trivial scalar field. So it is interesting from that point of view. Now, in the context of the Einstein scalar Gauss-Bonnet, we looked also for these type of solutions, hoping that we will find regular solutions, no singularities, no horizons, no throws. We kept more or less the same answers for the metric, and we looked for regular black hole solutions, and indeed, we found solutions where at smaller distances, and I'm naming here a particular choice for the coupling function, which was the quadratic form. We found that both metric functions, I'm just showing one of the two here, A is just a polynomial in terms of the radial coordinate. Phi, it's a combined form. It has a polynomial in terms of R, but also a singular term. Now, that might create some worries. However, let me go on to present some plots. I have here curves. Now, the solid curves are the GRR. As you can see, it is always finite. We have no divergences. Phi, of course, goes asymptotically to a constant, but close at small values of R, it goes to plus or minus infinity, depending on the value of C0. Although this is worrying, it doesn't create any singularities, either in gravitational quantities or in the energy momentum tensor. And you can see here the 0,0 component. It presents a spike where I have a localized object, if you like, but then both towards 0 and both towards R infinity, the energy momentum tensor, rho, the energy density, keeps finite values. And I can give here the asymptotic values.
Sorry, Yoda, can I ask something?
Yes, of course.
So the limit to GR is not smooth, right? So if you take alpha, go to 0, there's not a smooth transition, right? There is
in this case, no. For a regular solution, no. If you just wipe out the Gauss-Bonnet term, because that would do, I mean, if you just put alpha equals 0, exactly, then you don't get a limit. You go to the singular limit.
Good.
Where G is also divergent at some point. Indeed, you must keep alpha always different from 0.
Panagiota, may I ask also one more question? Could you please go a little upward to the previous?
Yeah, here.
Oh, no, here. This is a solution. A regular space-time, no singularities, no horizon, no throats, but you say it is asymptotically flat?
Yes, it is. It has exactly the same asymptotic behavior as the black holes and the wormholes. So if you look at it from far away and you check only the asymptotic behavior, you cannot see any differences.
Well,
quantitative, yes, but qualitative, no. I mean, depending on this is the small R expansion.
Yeah, the question is actually the component, let's say GTT, is an exponential function of A of R.
Yes.
You expand here and you have an A0 plus A2R squared, etc.
Yes.
In case you have an asymptotic flat, if I remember well, at infinity, this is supposed to be 1.
Yes.
Minus 1, actually.
Yes, of course.
Is that so?
It should be, yes.
It should be.
What we get, yes.
But as it is now, as I see that,
No. It's a different expansion. This is only the expansion at small distances. So we go to the field equations and we say we write an expansion in terms of r for small r because we want to be analytic. So if you take the expansion close to r equals 0, then you will write a power series expansion in terms of r. We also included the linear order term, of course, the alpha 1 times r, but that has to be 0. If
okay,
you substitute,
but you have the A naught. You have the A naught. The first,
yes,
you have an A.
that's
Okay.
just constant, which you can include it in the redefinition of the time coordinate. Now, if you're interested in the large R expansion, then you will start with a different expansion in terms of 1 over R.
Yeah, but then you have to also redefine the B, and you have to redefine the ds square.
Yes.
You have to redefine the whole metric. Well,
yes, indeed. This is not the solution valid at large R. No, this at some point stops being valid. In the same sense, the power, the 1 over R power expansion at infinity is not valid for small r. You have 2 different expansions.
okay, agree.
Whereas
Okay.
in the black hole, I had the expansion in terms of r minus r age close to the horizon, and then I had 1 over r power expansion at infinity, and the 2 had somehow to be smoothly matched somewhere in between. This is, I'm assuming here. I have the 1 over r expansion at infinity, and I have polynomial expansion at small r, and the 2 need to somehow be smoothly completed, matched, in order to produce a complete solution. So this is only the small r. As soon as I start going outwards, that solution is not satisfactory anymore. I have to go to the actual numerical solution that will take me finally at the asymptotic regime at infinity.
Well, what about the geometrical, let's say, symmetries, like the time-like vectors or the space-like vectors or something, a killing vector? The only thing that I can see, it's only the T. Am I right? What kind of killing vectors do you shall have in the metric with the scalar field phi?
Well, in this case,
certainly you have the T killing vector. What about the others? I mean, the R and the phi, the theta. Do you have symmetries here?
Yes, of course. We would have the same symmetries as before.
But I mean, you have killing vectors here.
Yes, why not? I don't see any problem with that.
Well, at the first view, it gives me the impression, I came to the impression that you have only one killing vector, the T.
But we don't have any, I mean, this is spherically symmetric.
Phi.
It is a spherically symmetric metric, right? I have the dependence only on R. So I should have 2 conserved quantities, the energy and the angular momentum of any field that I'm considering propagating. Well, I will come actually to the propagation of fields.
Okay.
In my last transparencies, actually.
Okay.
And then because there we have some nice observable effects.
Okay.
Okay, so if I go back to the form of the solutions, so just to conclude that although we have a singularity at the scalar field close to r equals 0, not at infinity, but close at r equals 0, this 0, 0, the actual energy density remains always finite, and it creates like a shell-like behavior for this particular object. And that qualifies these objects as ultra-compact because very soon after we start moving outwards, that energy momentum tensor vanishes and we get an asymptotically flat limit. That's why we call these objects ultra-compact objects. And a similar behavior was found by these people in a paper, in a recent paper, for the case of the exponential coupling function. Here we found that this behavior persists for all forms of the coupling function. And now actually the last transparency with some nice observable effects. Now, if we like to study the propagation of particles in this background, so we studied both null and time-like trajectories. Let me stick to the photons because this is where we have some interesting effects. In order to study the photons, we should consider ds squared equals 0, or we take this combination to be 0. And if we work out slightly, this one is just one line calculation, we may find the effective potential that photons see while they're propagating in this particle-like background we found. And we plot the effective potential, which is this one. And as you can see, there are extrema in the form of the potential. There is a local minimum and there is a local maximum. We have considered different lines because there are different solutions with a variety of parameters. That's what, in order to show that this is actually a generic behavior for the quadratic coupling function. And that is the form of the effective potential. It is, sorry, this is A minus B in the notation I've used before, over 2, so that it's the two metric functions, one over the other, and the square root times r, the radial coordinate. And they present two extrema. The one which is a local minimum is a stable one. The one which is a local maximum is an unstable one. But every extrema of the potential corresponds to a circular orbit for the photons. Therefore, we have light rings around these ultra-compact objects, which is rather interesting. So whenever we have photons propagating in the ground, we can have bound orbits. They can actually be captured by the gravitational background and form light rings around the Yuccos, and that would be an interesting observable. And something else. If we consider the scattering of a particle that comes from a very large distance, travels and propagates inside this particular background and then escapes again to infinity. Well, we had in mind the gravitational waves, but we took a scalar field as a prototype model. If you start and write quite easily, it's the Dalabersian on psi. I'm calling psi not to confuse it with phi, which was the scalar field of the theory. But now I have a test particle, psi, scalar again. So if I take its equation of motion, which is fairly simple, I can find the effective potential for this type, for test particles propagating in this background, and I plot it here. We can see, again, we have different curves for different backgrounds. So if you focus on one of it, let's say the blue one, you can see that the effective potential presents a local barrier, and then it goes up to an infinite height barrier. And this is typical for all the solutions of this type. If you consider the different parameters, then you just have a local barrier and an infinite. So all these curves join into this infinite height barrier here. So what happens is that now consider a scalar field falling into this, approaching the r equals 0 regime. What will happen is that it will partly reflected by this barrier. So part of it will be reflected and propagate to infinity, but part of it will be transmitted. When it gets inside this small area, then what will happen is that it will propagate towards the infinite height barrier, and there it will be totally reflected. It cannot go inside, of course, because it's an infinite height barrier. So its direction of motion will be reversed. When it comes here, it will be partly reflected and partly transmitted. And that, for the part that stays between the two barriers, will go back and forth, and each time part of the scalar wave gets transmitted, it will give an identical wave signal at infinity when an observer is. And that will create echoes, as we say, in the wave signal, which is another interesting observable associated only with these Yuccos that have no horizon and no singularity inside, but they do have an infinite height barrier here. And therefore, this kind of behavior will never take place, let's say, near black hole. Because for this Schwarzschild, let's say, hole, we do have a local barrier, but then this local barrier goes to 0. We don't have this infinite height. So whenever it gets inside, it will travel to the singularity and then it will get absorbed. We will not have these echoes in the wave signal. Okay, let me conclude because I went over my time. The generalized or alternative or modified theories of gravity may be the way forward in gravitational physics. It is definitely one direction of research that deserves studying. The Einstein scalar Gauss-Bonnet theory that I have considered here is a very promising type of a quadratic theory because it admits a variety of solutions. And I have here the zoo, as we usually call it, of the different type of solutions that we get in this theory. So we get particle-like, we have wormholes, we have particle-like with throat and an equator, something that I didn't mention, but we can also have. But inside it's not a wormhole, it's a regular particle-like, or particle-like ordinary with no throats and no equators. And here, the dark line is the black holes in this particular family of solutions. That is for one particular function f. It's the phi square, for example. Therefore, the solution space contains regular black holes, wormholes, with no need for exotic matter, and particle-like solutions with different characteristics. All of these have scalar here. They are scalarized solutions in the natural sense. They have the scalar field for all values of their parameters, and of course, for arbitrary coupling function. So that's why we focused during the last years on the study of this particular theory. And the question comes up, what else could there be in this phase space of solutions? Well, we don't really know, but you may observe that there are still white spaces which have not been covered or investigated. So soon or later, these things, new things may be discovered. Thank you very much for your attention.
Thank you, Panagiota. I see that Vasilis wants to ask a question. Thanks very much for the talk. Okay, Vasilis, please ask question, and if anybody else wants, they can straight away address the question to Panagiota to wait for me.
Well, Mrs. Kanti, thank you very much for the interesting presentation. I'm not very familiar with Einstein scalar Gauss-Bonnet theory. So I have a few questions. Well, I have several questions, but I'll ask only two. First, about the last all kinds of objects that you presented, the ultra-compact objects that are particle-like. Do we have any sense for the stability of these kinds of solutions? In principle, it shouldn't be difficult to study the stability of these objects against radial perturbations or something like that. So that's question one. I don't know if you'd like to address the question, then I can ask my second, or I can ask my second question at the same time. It's up to you.
I can offer an answer which is actually very, very brief, that we haven't studied the stability. We have done a little bit on the stability of black holes and the stability of wormholes, but we haven't studied the stability of this type of solutions, the particle-like solutions.
Okay.
I can't really say, and because there are very few particle-like solutions in the literature, there's no really, an association or a limit that we can, that our solutions reduce to, so that in order to be able to draw some, some conclusions, even without studying, let's say, the particular solution. So I really don't know if they're stable under an arbitrary type of perturbation. So you may proceed to your second question.
Okay. The second question is, just like any theory of gravity that is not general relativity, it has to pass a certain set of tests. Solar system tests, binary pulsar tests. Since there's a scalar field, there should be dipole radiation in this theory, and there are so strong constraints and dipole radiation. So I'm just curious, within the context of the f of phi coupling functions, if you consider what kind of limits there are on the constants that enter in the coupling function.
Yes.
And how do these limits translate to masses of black holes that may be relevant for maybe seeing some interesting deviation from general relativity from the gravitational wave point of view?
Mm-hmm. Okay, yes, a very good question. Thank you. Indeed, we have constraints. Okay, it is a modified theory of gravity, so we should take some constraints. Now, concerning the scalar dipole radiation, well, in that case, I have assumed here that the scalar field has absolutely no mass, it's massless. Therefore, if you perturb the space-time, you should get scalar dipole radiation. That you may evade or avoid if you just introduce some kind of potential. Because in the case that I introduced the potential, you saw that the scalar field just goes to zero completely and disappears at large distances. If you give a mass, which is another case, if you just give a mass, then you're not supposed to see that at very large distances. The dipole radiation, as far as I know, goes away. But of course, that doesn't mean that the scalar field is not there. The scalar field will have couplings with the gravity, and of course, it will modify several things like the spectrum of the gravitational waves. And that's why, even implicitly, we hope to get constraints from strong gravity experiments when it comes to the allowed values of the parameters. Now, I do have a few transparencies on that. Let me concentrate on some of the important things. Now, one important thing, because you mentioned the masses of the black hole, I said that black holes have a minimum mass and a minimum horizon, the Gauss-Bonnet, not the Schwarzschild, the Gauss-Bonnet. And therefore, the question comes, okay, so if I demand that the black holes that I have already observed in nature fit into this particular constraint, what do I get for the coupling function? So as I said, I define alpha, which is a dimension for the coupling constant that says how important is the coupling between phi and the Gauss-Bonnet term. If I use that alpha as the coupling constant on which I have to put bounds, then if I use that, we have certainly, and that is a relaxed bound, it can go below that. If I demand that we have certainly black holes with a mass as low as 5 times solar mass, you can go even lower than that, then you do get a constraint that the square root of alpha, in order to be 1 over L, or in terms of mass, is 6.2 to the 5 centimeters. And that is one constraint that I take just by demanding that the minimum mass black hole predicted by the theory fits with the observed black holes that I see in nature. Now, that is not a very strong one. Remember, the scale is 10 to the 5 centimeters, okay? It's still very high up compared to the 0 value for alpha, in which case the Gauss-Bonnet would go away, and I'm going back to the more or less GR. Of course, there are many more constraints. Bounds from the solar system, well, 10 to the 13, okay? It's very relaxed because the field is very weak at the solar system level. Bounds from quasi-normal modes, they are still in the order of 10 to the 5 centimeters. So even if I observe quasi-normal modes from the merger of black holes, for example, it won't lower this constraint much. If the Einstein telescope, if we take measurements from the Einstein telescope, that will do better, okay? It will decrease, it will make more stronger the constraint for alpha. And we have other, of course, from the speed of gravitational waves. Not much a localized solution, a gravitational localized. And any deviation in the speed of gravitational waves goes down like 1 over r to the 3rd. So the farther away you go from the source of the gravitational waves, any effect on the speed of the gravitational waves compared to the speed of light just dies out. That is 10 to the minus 50, let's say. It's an extremely small number because it is proportional to d, the scalar charge, which is not particularly large, okay? The larger the mass you have, all the sightings that we have from the gravitational waves are fairly large astrophysical bodies. The black holes are 25, 30, 40, 80 black hole masses. The scalar charge for these objects is extremely small. That's why this quantity here will be very, very small. We have actually many more constraints that give something which is of the same order, 10 to the 5 centimeters. What I read quite recently, and this is the last thing in my answered is that, of course, we have also bounds now from the Event Horizon Telescope, okay, by observing the black hole shadow of the M87 black hole. And they have actually produced some results whenever they consider some particular modified black hole solutions. They found that the deviation in the shape of the black hole shadow would be beyond any agreement with the observations. To be honest, I haven't seen any analysis done for this particular type, and I haven't had the time actually to look at myself and see what bound on alpha these particular constraints would imply. But I haven't seen any really radically and extremely strong constraint on alpha yet that has come out from the Event Horizon Telescope. So that's the situation actually up to now concerning the bounds that we have on alpha. It is far from excluded. That is actually the conclusion.
Right. So my question is not so much about being excluded, but I'm interested in whether the range that is allowed right now, it is such that it would make, let's say, the LIGO black holes that are 30, 50, 20 solar masses, interesting to look for deviations, because these tend to be, I mean, if I understood, there's this 5 solar mass argument that you made that places 10 to the 5, order of magnitude 10 to the 5. So is it really that we will expect deviations from general relativity in this theory for these smaller mass black holes? Do we expect to see anything for these 20, 30 solar mass black holes that like?
Well, I would say no. No. And the consensus is that the gravitational waves observed by LIGO and Virgo cannot place strong bounds on this type of theories.
Thank
at
you.
this point, at least.
Can I ask a couple of questions myself?
Of course, go ahead.
Right. First of all, thank you, Jota, for this wonderful talk. It was really nice. Okay, I have a couple of my questions were already answered. The bound from the neutron star merger, for example. If we consider primordial black holes, which are actually formed in the early universe, and they can be actually very small, but if your alpha is actually also small, they might be also out, right? Gauss-Bonnet primordial black holes. The thing with them is that they undergo process of gradual evaporation, all right? So their mass is actually decreasing. At some point, it will hit the lower bound mass that you have. What happens then? Is the black hole stabilized? Because a Schwarzschild black hole would actually evaporate completely. And then, but if stabilized, it could be a potential dark matter candidate, for example. Have you thought of that?
Well, we have looked at what happens close to that minimum. Now, what actually happens is that if you decrease too much the black hole mass, then that means that you increase the curvature of the space-time and you increase the effect of the Gauss-Bonnet term. Because the Gauss-Bonnet term has a negative contribution to the energy density of the system, that makes extremely difficult the creation of the black hole. So up to a point, well, this is actually a fight. Whenever you have a Gauss-Bonnet term, there's actually a fight in the theory in order to create a black hole. The rich scalar tries to attract matter and collapse matter and create a black hole. It is the traditional gravity behavior. The Gauss-Bonnet tends actually to push that matter outwards. And whenever there is an equilibrium between two, the whole thing works, and despite the presence of the Gauss-Bonnet, a black hole forms. But if you decrease the mass of the black hole a lot, and therefore you increase the curvature of the space-time, then the Gauss-Bonnet term becomes really dominant. The repulsive force becomes more dominant than the attractive one, and then you cannot even form a regular black hole horizon. Okay, the black hole horizon ceases to exist. Right. In very much the same way, for example, that if you have too much rotation or too much electric charge, you don't get an event horizon in the case of the Kerr or of the Wessner-Nordstrom case. The same thing more or less happens here. Okay? And therefore, if you go further down, that is why if you decrease very much the mass of the black hole, you don't really get a solution. It is an interesting question what happens if you start with a primordial black hole, which is a Gauss-Bonnet. because as we say, all small black holes are found to be Gauss-Bonnet, and during their evaporation process, their mass becomes smaller and smaller. Then when they hit the barrier, okay, the minimum mass, then it's not a black hole anymore. I don't really know what it is, okay? We have discussed this, you know, in workshops where people working on this type of black holes just got and, you know, they just exchange opinions about problems and things. And even people working for many years now, this type of black holes, do not really know what happens then. It's a different type of object. It is not a black hole anymore. Now, whether you end up with a different, that's why I'm saying that we should look a bit more into what exists in the phase space of the solutions of this theory. Because a very prominent question is exactly that. When we have a process, a dynamical process that reduces the mass of the black hole beyond this minimum limit, what happens then? It is not a black hole anymore. I don't know. It is not stable. I wouldn't say that it is stable, because from the entropy plot I showed you, you may conclude that for most of the families of black holes that we have found, the larger part is the stable one, the ones that have masses closer to the Schwarzschild. When you go to the small mass regime, then we have families which are really stable, but most of the families really get unstable as we approach the minimum mass limit. And this is more or less understandable, because as the fight goes on between the Ricci and the scalar and the Gaussian, when you approach this regime, then it's more difficult to keep this balance. So a little perturbation, a small perturbation, may destroy the whole thing.
The fact that
I don't know what happens if it's something else. I would say that the black hole changes to something else.
Yes, but the question is whether this something else is a stable or not. A dark matter candidate.
Of course it
because this regime, this parameter space is actually chopped off, because everybody assumes that the black holes evaporate and therefore they cannot be the dark matter. All right, but if they cannot evaporate and they give rise to some kind of stable object, then this could be a dark matter candidate.
Of course.
Okay, that's one question.
This is why all these solutions, I mean, you can see that we have wormholes, for example. This is the family of black holes. Right here, it stops because of the minimum mass, but then close to it, there are particle light and the wormholes, okay? So maybe there is a transition to one of these solutions. Maybe it's something else, it's a naked singularity. I don't really know. And in order to study the stability, you must know to which solution you go to.
Okay, thank you. Second question. Suppose that this scalar field that you actually involve in is the Higgs field, the electric Higgs field, okay?
Yes.
Then how is particle production process on the event horizon of the black hole is going to be affected? Because now, of course, the expectation value of the Higgs field is very important in terms of the masses of the particles, and the masses of the particles are crucial with respect to whether they get particle produced or not. Okay, because if they are heavy, they are not. Okay, so if the whole process is affected, then I presume also the Hawking temperature will be affected, and the whole process of evaporation is affected. Have you looked into that?
No. We have a question. If you consider a Higgs particle, then of course you have to introduce a potential that has the particular form. I don't think that would be a problem, because we have checked many different types of the potential of the scalar field, and most of them, in most of these cases, we have actually ended up with a solution. Now, the value of the field itself doesn't seem to be particularly important. It seems that as long as you are above this limit for the minimum mass, which you can easily change by choosing the value of the coupling function and a corresponding value for the scalar field, then you do end up with a solution. So I wouldn't say that introducing such a potential would be a problem, but to be honest, we haven't looked at that particular combination, because the Higgs field demands a very particular type of potential.
Okay, but it might have interesting physical repercussions. And finally, okay, my last question doesn't have to do with black holes. But when you discussed the wormholes, you talked about the Morrison-Thorne wormhole, which requires this exotic matter, and how this is possible to realize in the Einstein Scalar-Gauss-Bonnet theory. All right. This exotic matter in cosmology is also called phantom dark energy. All right. So what you really said there is that if the theory of gravity was Einstein Scalar-Gauss-Bonnet, then we might have a candidate for phantom dark energy. And if you have phantom dark energy dominating, you end up with a big or some cataclysmic singularity. I think this is something worth investigating. Have you actually considered looking into something like that?
No, I mean, the scalar field is not, the scalar field that we have introduced by itself is not a phantom field. So the total energy momentum tensor receives contribution from the scalar field and from the Gauss-Bonnet term. Mm-hmm. And what happens is that although the scalar field remains a physically acceptable, a canonical, a physical scalar field, the contribution from the Gauss-Bonnet term, from the coupling between Gauss-Bonnet and the scalar field, if you like, from the potential, in a way, it's the thing that creates the negative energy. Okay, so it is actually...
But as far as the universe is concerned, it's the whole thing that matters, right? Because the source for the dynamics of the universe is the entire energy momentum tensor. So if the energy momentum tensor is, of course, has the part of the scalar field, which is a regular scalar field, as you mentioned, but also has the Gauss-Bonnet part, all right? And the whole thing behaves like phantom dark energy. Basically, the whole thing works. And it's even better that the scalar field is actually a normal scalar field, is not a crazy scalar field.
Yes, naturally. One could consider that direction as well, but you have to introduce time dependence in the field, which we don't consider here.
Yes.
They're just, localized, only radially dependent configurations for the scalar field and the metric. Okay, so you would have actually to change this whole thing, and then I don't know what happens with the constraints in that case. If you allow phi to be a time dependent, if you allow Gauss-Bonnet to be, dominant in its way over the whole universe, then I would expect that you end up with very severe constraints.
Okay, but it's interesting to investigate because it's difficult to form realistic candidates for phantom dark energy. So that's a promising direction.
It is a first step, definitely, yes. I agree.
Thank you.
You're welcome.
I think Thomas was...
Yes, I see
this finger.
Raised hand, yeah.
Hi, Dr. Thanks for the nice talk. I just wanted to make a comment in response to Vasilis's question and the detectability with gravitational waves. I mean, I definitely agree with what you said, but I wanted to add that in the specific subset of models within the class you're able to get from current future gravitational wave detection. So in specific, if you think of your action as an effective theory, then there are lower order operators basically that have not been included, which even though they do not generate hair, they would actually change the charge, the scalar charge that your black holes would have, and hence control the scalar charge, and also would have an effect on whether you would have a scalar charge for neutron stars. This is particularly true for models that allow for spontaneous scalarization, where you don't have charge threshold above a mass threshold, and you have charge below. And hence, it is possible to kind of arrange the signs of your coupling constants for operators that should be there, basically, in such a way where neutron stars do not have any scalar hair. Basically, they have trivial scalar around them. Hence, you can take dipolar emissions from the binary pulsar and so on and so forth. Whereas black holes below certain mass threshold would have scalar hair, And hence, you could already try to read off constraints from existing gravitational wave observations. People have not actually done that yet, but you could read off constraints from the coupling. So in a sense, we could kind of do better in constraining these couplings already with existing and with future observations. And another two related points that you could actually also arrange your signs of your coupling constants in such a way where the scalar hair is actually triggered by rotation. So you have rotating black holes which are non-charged under the scalar, and they just charge in rotation, which again, you know, at least existing constraints do not apply directly, but technically speaking, they're already constrained effectively. And we don't know what the constraints are from existing gravitational wave observations if you assume that the black holes in the binaries are rotating. And one final kind of more heuristic comment is that in principle, you know, this kind of spontaneous scalarization theory show you something else as well, that there is a possibility. You have a scalar field that is basically sourced by nonlinearity. So there is a possibility that you could put your theory together in such a way that even though your black holes don't really have permanent hair, I mean, this is not examined, I guess, but in principle, when they enter that kind of nonlinear merger phase, the scalar field gets excited and then gets de-excited again after the merger. So in principle, you could have some sort of gravitational wave signature as a transient that has not been modeled, and you could potentially find, even if your objects, you know, in the quiescent state don't carry any charge.
Mm-hmm. Yeah, of course, we welcome any kind of bounds coming from gravitational waves, and if we see any deviation, then that will be much more interesting. But even if we don't see any deviations, then it is a very useful bound. We want to know to which direction we can move in building an effective gravitational theory. And if something is excluded, it's very good to know so that we can move somewhere else. Yes, thank you very much for my very interesting comments.
Yoda, may I ask you something also?
Yes, of course. Go ahead.
First of all, let me make a comment that the important thing of the whole analysis is exactly what you're writing there, that you do not need exotic form of matter, because wormhole solutions exist in many theories, but almost always you have to consider very peculiar profiles for the energy density of the perfect fluid in order to be consistent. But here, it's the geometry itself that gives you this new structure. Actually, my questions have been already answered, but just a detail concerning the gravitational wave speed in these kinds of theories, because we know that a non-trivial combination of the Gauss bond, I mean, apart from the topological invariant, actually the graviton propagator gets dressed by the scalar field. So this gives you a kind of a different speed from the light speed. So I was wondering what you showed in the end is the perturbation analysis of the gravitational wave speed is performed around the spherically symmetric metric, or because strictly speaking, one should do that in a homogeneous anisotropic geometry. So to study the gravitational waves propagating in an FRW metric, and I think there is where some people claim that so this result here, I mean, is, as you said, is around the local solution, right?
It's around the local solution. So you could actually try to derive an idea, you know, a naive limit, if you just go to the result, to the constraint, the corresponding equation in the case of the maximally symmetric cosmological setup. But it is not the accurate one, because what you want is you want actually to make a perturbation around the gravitational solution. Exactly. And then there was actually a study, we didn't know at the beginning, we discovered it a bit later, already from 2012 by Kobayashi, Motohashi, and Suyama, which did this particular, who did this particular computation, and this is the perturbation around the gravitational solution. So I find that to be exactly what you need if you want to to see what kind of gravitational waves are produced whenever a localized solution is. Of course, that one then would need to travel inside the universe.
Exactly.
So at some point it will move away from this background, and then it will maybe adapt a different profile, and then again get detected close to another gravitational source. I don't know if the whole thing of that has been studied from the beginning, from the point of the production of the gravitational wave up to the point of the detection, while the whole thing changes. I don't know how easy that could be, but that is the study around the localized gravitational solution. So it takes the whole form of the space-time into account in its smallest detail.
Yeah, very good. Now, this is of course the result, but in cosmology, and this is, and I will end with that. This is what Costa said. In cosmology, you get also very interesting effective phenomena. And for example, even if the scalar field here is canonical, effectively the effective dark energy can lie in the phantom regime, which is very good. So the combination with the geometry, with the Gauss-Bonnet term, can give you this nice new phenomena.
Yes,
okay.
it did.
Thank you. Thank you.
You're welcome.
Are there any more questions? Jota, I wanted to ask you just a very simple question. Because the fact that you have a minimum mass is a bit like what we would have for when we put rotation or we have rise and nostrum, typical of an inner horizon. Do you know if there is an inner horizon in these Gauss-Bonnet black holes? So there's a turning over at some point for the function.
Well, because we found the solutions numerically integrated, and we use a coordinate system that stops at the horizon, at the event horizon, which is the external one, we don't really know what happens in between. If we change the coordinate system, then one could maybe enter.
It must be there is an inner horizon, and maybe there is an extremal case.
Maybe. I simply don't know. Because numerically we stopped at the horizon. Well, actually we started from the horizon and we moved outwards. We could do the opposite though, by giving the appropriate boundary conditions and integrating inwards.
Also, you said that, so the horizon size is when alpha is positive, is smaller than the Schwarzschild radius? It gets, I mean...
Yes. For alpha positive, yeah, it gets smaller. Because of the Gauss-Bonnet, as I said, the Gauss-Bonnet is repulsive. Yeah. In order for the black hole to be created, you have to squeeze it into a smaller area in order to create a black hole.
Right. So if you had some, what you call a photon ring, you were saying for the particle.
Photon ring, that was for the particle-like solutions.
That's like we do for Schwarzschild, where we have it, I don't remember the name, R equal to 3m, where we have the last, unstable photon ring or spherical. It's basically more or less what is creating the shadow.
So the unstable circular orbit. That's what you mean? It's called,
well, for light. So I guess your light, your corresponding last unstable light spherical, whatever ring that you're going to have, is going to be smaller than the Schwarzschild one. So exactly. So maybe this, if this is a strong enough effect, this would have some. You could get some constraint on alpha from the Event Horizon Telescope, for example, or in the future.
Yeah, for the same mass, the Gauss-Bonnet black hole would be smaller compared to the Schwarzschild, and therefore all the effects around it would be much more localized to a smaller radius. Right. So yes.
So I can put more mass in with the Gauss-Bonnet, in fact.
Yes.
All right. So,
yeah, I have a question. Have you ever tried to do some kind of tensor perturbations on your scalarized solutions, in the sense that this will give you information if a real heavy black hole is formed, and it's not just a transient state that never forms a compact object?
Well, we have considered radial perturbations, coupled radial perturbations, the scalar field with the tensor. So we perturbed the metric functions and scalar field. And because they are all coupled, we considered the coupled system. And we found that whenever you change the form of the coupling function, the stability may be completely different. Therefore, the exponential, the dilatonic black holes, the old ones back from 1996, we did the perturbation then, and we found that they were linearly stable. So even if you perturb those, they survive, at least the radial perturbations, okay, in the linear approximation. And there were other groups who studied actually the stability in a numerical way, and they found the same result. There were Cardoso and Pani, if I remember correctly.
You mean in the presence of the Gauss-Bonnet term coupled to scalar field?
Yes, of course, the complete, okay? So numerically, we did it semi-classically, actually, by seeing whether we can find, modes with a negative frequency and all that stuff. But then people who did a very careful numerical analysis looked at the same thing, and they found, again, linear stability of these particular solutions. But it is not a common behavior of these type black holes. For example, if you consider a phi squared, they are not linearly stable.
But it will depend upon the coupling of this coupling of the scalar field to the Bonnet.
Exactly. This is what people have found, that for different coupling functions, you have different families, and they may exhibit a completely different behavior. So we need to isolate, to find out, to determine which are the stable families, and that might give us some information about the preferred coupling function. Because as they are right now, there is absolutely no preference.
Okay, thank you.
Panagiota, greetings from Thessaloniki. Very interesting talk. Hi. So I just want to comment on this gravitational wave speed you have on your screen. So it depends on the distance in an inverse third power law. I'm more or less familiar with the tensor perturbations at the cosmological level, which gravitational waves are mainly linear. So they have a specific amplitude and they don't depend on the, there is no notion of distance. So how is the gravitational wave speed determined in this kind of frameworks? You linearly perturb the metric maybe of the compact object? I'm not sure.
Yes, this is how you do it. Well, in the usual way, just that you don't perturb it around, a maximally symmetric space-time where the dependence is only on time. But here you perturb it in a radially symmetric, in a spherically symmetric, actually, only radially dependent background. So you perturb exactly the metric, I don't. Yeah, of course, the scalar field as well, if I remember correctly, but then you focus on the tensor perturbations, trying to find the equation for the perturbed, metric components. At the end, this is one you add up. I can't really remember the exact details, to be honest. It was quite some time that I read the paper. But I think that it reminded me very much of what we had done back in the 97, 98, when we check the perturbation of the dilatonic black holes.
Okay.
So you end up with the radial dependence, actually. That is the important thing. The time dependence, just you parameterize it in a particular way, then you end up again with the radial dependence.
Okay, thank you.
You're welcome. I see Thomas has another question.
I just wanted to say that I think if I remember right, both the exponential coupling and the linear coupling, the solution, the singularity is sitting at an article constant surface in the interior, and that is basically a space-like surface in the interior. So probably there is no inner horizon in response to Christos's question. Yes. I've never actually done the space-time diagram or tried to look in any detail, but that's what the fact that the singularity seems to be space-like suggests that there's no inner horizon.
I remember that there is a singularity. You continue the integration inside, but I had no no idea whether the horizon exists before that. Yeah.
This is a singularity because of the square root? Is that what you mean?
Yeah, I mean, well, it is, but it is a curvature. It turns into a curvature singularity if you go beyond decoupling. So it's sitting at some constant rate. I mean, in spherical symmetry for the exponential and the linear coupling, at least. The other, I don't know what happens for the other couplings, but it's sitting at a constant R surface, which has now turned space-like once you cross the horizon. And I think there is no inner horizon. That, you know, I mean, I'm guessing. You know, don't take that too seriously, but I'm guessing that you'd get a diagram which would be very conformal diagram, which would be very similar to the standard Penrose diagram of Schwarzschild, except the singularity would not be at R equals 0, but it would be at a larger radius.
Mm-hmm. If space like, then there shouldn't be any horizon in between.
Yeah.
Indeed. Mm-hmm.
Right. So maybe we should stop the session and thank Panagiota again.
Thank you.
Was there any other question? I heard something just before, but I guess it was maybe Thomas switching off his microphone. Okay. Thanks a lot, everyone. It was a very nice talk and a very interesting discussion we had today. We will continue next month. I think it's Lampedakis who is giving the next talk about the end of April. You will, of course, receive information from us later on this month. Okay, well, not this month, but the next one. All right. Οπότε δεν ξέρω γιατί μιλάω στα αγγλικά, επειδή συνήθισα, αλλά για όλο τον κόσμο. Ευχαριστούμε πολύ, Παναγιώτα. Τα λέμε σύντομα.
Ευχαριστούμε, Παναγιώτα. Ευχαριστούμε.
Ευχαριστώ και εγώ. Να είστε καλά.